Hey everyone, welcome back to the show. Today we are diving into something that might just change how you think about running applications in the cloud. We are talking unikernels and NanoVMs with Ian Iberg, one of the founders of NanoVMs. Now I know what you are thinking. Another buzzword in the already crowded cloud space. But here's the thing, this isn't just about another incremental improvement. We are talking about fundamentally rethinking how we run software. Think about it. Linux is over 30 years old, built for the time when multiple users needed to share one massive machine, expensive machine. But today, you spin up a VM on AWS that costs pennies just to run a single application. Yet, we are still carrying around all that multi user, multi process baggage from the 1970s. In this episode, Ian breaks down why this matters more than you might think. We'll cover the security nightmare hiding in plain sight, why container escapes happen so frequently while hypervisor escapes are rare, the performance tax you're paying and you probably don't even realize it, how unikernels are different from containers, micro VMs, and everything else you've heard about. Real talk about limitations, what works, what doesn't, and what might never work. The ops burden you could eliminate. Imagine deploying without managing all those YAML files. Ian comes from the security world, so he doesn't sugarcoat the challenges. But he also shows how some companies are already seeing dramatic improvements in performance, security, and operational simplicity. Whether you're dealing with Kubernetes complexity, worried about container security, or just curious about what comes after Docker, this conversation will give you a fresh perspective on cloud infrastructure. So grab your coffee and let's dig into why sometimes the solution isn't adding another layer. It's actually stripping everything back to what you actually need. If you like this discussion, don't forget to hit the like button and subscribe to the channel. Hello, welcome Ian. I'm really excited to have you today. Thanks for accepting my invite. This topic for today was on my list since last year, and somehow I finally got to it and reached out to you. And I'm excited that we are talking about unikernels, nano VMs, and all this around technology today. So welcome to the show. Thanks for joining. I would love for you to start with an introduction about yourself, a little bit about your background, and how did you end up founding NanoVMs?
Yeah, thanks first for having us. This is a really interesting show. I had to watch a few episodes to kind of catch up and see what it was all about, and it's pretty cool. Yeah, so my name's Ian Iberg, one of the founders of NanoVMs, and I guess briefly to how I got kind of involved in this was I come from the world of security, so have been involved in computer security companies and quote scene for many decades now. And so but it was around 2015, 2014, 2016, somewhere around that time that I started reading some of the papers about unikernels. And it kind of dawned on me that that from a security point of view, they had a lot of interesting potential, and that just made me dive kind of further and further into it. However, there were quite a few different issues with some of the proposals that people had about them. One was a lot of the projects were kind of stuck in academia, which makes sense. I mean, if you're reading a paper, it's all coming from academia, right?
Yeah.
And the problem with academic papers in general is the gulf from somebody writing a paper to like something that's commercialized and available for your average developer to use is insanely large. It can easily be measured in a decade. Other examples you can look at, like the Databricks people, for instance, and when they started on their stuff like O5 or something. So that's pretty common. But yeah, I started getting more and more involved with unikernels, and at the time we were using rumprun and OSV, some other unikernel implementations that existed. However, not having a company built around them meant that we had to do the support We had to do the patches. We had to do all this work, and that's fine. But then, like, who actually owned it and who could drive the vision, right? And so that kind of became a pretty big force for us to start walking down the path of making our own kernel. And so that actually happened around 2018, I think, is when we started actually working on Nanos itself. And then it was closed source for a while, and maybe about a year before we opened it up. And we didn't really have a opinion on whether it was going to be closed or open or anything. It was just like it wasn't usable for for a while. So one thing that might be helpful for your audience is when they hear the term unikernel, they should just replace that with operating system. Because at the end of the day, that's what it is. It's a special type of operating system, but that should give you kind of a better idea of the scope of what these things are. Because a lot of people have this kind of mistaken notion that it's Docker 2.0 or something. And that's just, to me, that's a very wrong impression to have, because it implies that it's just some sort of little infrastructure project and boom, you have a unikernel. And that's totally not what it is. It's a replacement for running Linux in the cloud. So Linux is 30 plus years old and has untold, years of work behind it by thousands and thousands of people. There's probably like 60 or 70 maintainers in the current maintainers list, not all the people that get contributed, but the people that contributed regularly. So it's actually a pretty large undertaking at the end of the day. And that also kind of goes into the question of like, well, I've heard about unikernels, but like, what's the status? And, like who's using it? And it's, early adopters are the ones that really kind of get into it simply because of that gulf of like 30 years of existing development that Linux has on top of it. So I know I spewed quite a bit of stuff right there, but
no, we'll get to that.
Kind of take this whatever direction
you
want to go.
We'll get to that. And so you mentioned like security, you started with security, and that is the major advantages as per my reading. And then you also briefly described what is not unikernel. So, but we'll get to understanding what exactly is unikernel. I mean, you said it's an operating system, but we would love to have some deeper understanding there. Before we, go there, I guess, so as you mentioned, Linux is now, 30 years or more older than that. And probably it's not built for the modern applications deployed on cloud with modern requirements. And some innovation is needed to get rid of all those problems. And we'll get to the problems again. But talking about the historical timeline, how has the trend changed? If you mentioned 2016 when you read the unikernel paper. I guess 13, 14 was the Docker and Kubernetes era, and everything was on containerization and orchestration and on that direction. But if we go back a little bit further, what is the timeline like, and how did we reach to unikernel?
Yeah.
Yeah.
So and to me, there's kind of a broader story arc here that kind of explains the rise of it too. So it's now 2025. The year of this recording. And to me, you have to go all the way back to 1969 to really understand the story. So back then, 1969, we got Ken Thomas, Dennis Ritchie. They're co-creating Unix, and they're working on a PDP-7 or a PDP-11. So this is a computer that takes up an entire wall, cost $500,000. And so when they're designing Unix, which is basically what Linux is a derivative of it, they had to put certain design constraints into the operating system. So again, this is one machine that takes up an entire wall, cost $500,000. They needed the capability of having many different people come into the lab and run their programs on that computer. They had to share it, basically. There was no personal computer back then. There was no laptop or anything. It's like we have this big machine, everybody has to share it. And then they also need the notion of like, hey, we want to run many different programs by these people on that same computer. And so, you have that notion. So right off the bat, you have this multi-user, multi-process notion. And that concept lives to this day. 50 years later, we still have the exact same notion. Unfortunately, lots of other things have changed during the past 50 years. If we fast forward into 91, 92, you have Linus, and he's working on a 286. Maybe he's trying to work on a 386, and he creates a free version of Unix. So this is an interesting time period because at the time we had all the Unix wars. We had all these companies suing each other over the rights for commercial Unix variants. And so this concept of having a free version was actually a really powerful thing. This is where we saw some of the BSD's arc and lots of other activity in the space. But what was also special at this time was we had the first browsers starting to come online, Mosaic and so forth. And so, that rise of the internet boom really, really accelerated Linux, especially towards the later 90s. And so that was an incredibly special time. And then we hit the .com bust in 2001. And so this is interesting because people needed Linux at that time. Before then, they might have been using Solaris or some other commercial variant. But at that time, it's like, okay, we can't be paying these people anymore. We really need something that's free. And so what's really interesting is you have this company, VMware. And so they started actually commercializing virtualization. And virtualization had been around for many, many years, but nobody had really had almost like this consumer variant of it that was commercialized. They were the first company that really popped it up. And then you also had Citrix doing the same thing with Zen. And so it wasn't until then that we really could do what we were talking about, even though there had already been papers describing this architecture with exokernel and so forth. What we also had was, for the first time, we had SMP capable machines. So what this means is our CPUs, up until that time, they really only had one core, one thread to actually work on. And this is important because without it, virtualization didn't really make sense. And it kind of paved that path. So a few years after VMware had its deal, we had this small bookshop up in Seattle called Amazon. So we're talking 2005, 2006 now, and they start unleashing S3 and EC2. And what they essentially did was put an API on top of virtualization for developers to hit. This was another big kind of deal that happened to allow these things to rise. And so now, fast forward to now, we're swimming in a sea of virtualization. I don't care if you use containers or VMs or whatever, a lot of people are on the public clouds. And the public cloud is 100% virtualized, 100%. So it kind of begs the question of do you really need 2 layers of Linux to run an application when we already know that you're going to isolate each application merely for scaling purposes? So there's so many different confluences of things that were going on that kind of led to this. I mean, if you look at your typical database at, even a company that's maybe 50 employees or above, it doesn't even fit on one server anymore. They have to shard it out amongst different servers. They've got to add replication. That's other servers. It doesn't even fit on one server anymore. So this whole idea that we're going to have one server with 20 different apps on it, it's just a notion that doesn't even make sense in most tech companies today. And so we, again, just asked this question. And the question is, why do we have an operating system when it's going into a fake virtual machine, trying to manage all these different apps, but yet it's sitting on top of the hypervisor? Why not just isolate each application? And coming back to the security side of things, we can get rid of all sorts of security issues. The performance can increase dramatically. Your cost can go way down. There's so many different benefits to it. But people are so accustomed to the way of doing things, right? Again, Linux is 30 years old. Unix is 50 years old. So there's a little bit of a habit breaking change required for adoption there.
Mm-hmm. Makes sense. And I mean, it's a fascinating journey, right? And just if I have to distill what you have said there, basically the trend has been building one layer of abstraction on the other layer. And eventually on this path, we have created some application bloat, which is not really suitable for the modern application. And besides being just not suitable, it's also costly. It also is insecure because it increases the surface area, and it's slow, right? So performance, cost, and security, I think these three are the major ones.
Mm.
This probably gives us a good direction towards understanding what do we even mean by unikernels and how they are different from the Linux. And there are too many terminologies here as well. So would love to kind of get a basic understanding of each one of them. One is, of course, the Linux operating system. Then there was like a virtual machine, then Docker and Kubernetes, that containerization, and then there is popular these days, which is micro VM, and then the other one is unikernel. So what are these different things? Of course, some understanding is there about containerization and Linux operating system, but how do they relate to each other and what is different?
Sure. So the one of the more popular questions people have was, how are these different to containers, for instance? So at the end of the day, containers, they're a part of Linux. First and foremost, they're a part of Linux. So maybe some of your audience has seen Apple just released macOS container support, which is interesting that it took them so long, but that just shows you Cupertino's attitudes. But if you look at how they did it, again, it's still a small Linux VM, because containers are inherently Linux based. They use concepts like namespaces and C groups, and containers themselves have this kind of long history, but also that explains some motivation from people like me why we never liked them from a security perspective to begin with. So you start with groot. So groot, Bill Joy, all the way back in like 81 or something like that. This is the guy who wrote my favorite text editor, Vim. So he wrote groot, and groot was used a lot in like FTP daemons and so forth like that. But it was never, ever considered some sort of security boundary layer. In fact, you can go to the man page and it says this is not a security boundary. And then, namespaces and C groups were interesting. So C groups, this was something short for control groups. This was something that was largely developed at Google, and it was largely in response to VMware. A lot of people don't know this part. At the time, VMware and Google were kind of going head to head for talent. So this is mid 2000s. And obviously Google didn't want to pay that tax. But they wanted similar capabilities, specifically for job scheduling. And so they wanted the capabilities to set, resource limits and so forth for different jobs, make things a little bit more fair, scheduling that made sense. But if you go look at the C groups document, and it's on kernel.org, the version 1, it clearly says this is not a security boundary. Like, it was never meant for that. And I point this out because when you design things for one purpose, but then they get used for another purpose, that's not really the same thing as like when people say the V8 sandbox, for instance, which isolates JavaScript in the browser and so forth. That was designed for security purposes. And so it has many other benefits and guarantees that something that was not designed for security maybe doesn't consider. And so you really have to think these things through. Same thing like with gvisor. Gvisor was explicitly designed to deal with container security. And so it has certain guarantees that people were already thinking about before they even wrote code. And so containers, to this day, suffer hardcore from security issues. Just all the time, there's container breakouts. And some people might wonder why that's so prevalent, but a hypervisor escape is not so prevalent. And if you think about it, it's a really big deal because, again, how many of the companies that you talk to are on Amazon or Google Cloud or Azure? If we had hypervisor escapes as common as we did as container escapes, nobody would be using the public cloud at all, but everybody does use the public cloud. And so it really kind of begs the question there. Again, with containers, I mentioned namespaces, but there's 7 different types of namespaces. Again, these things were just kind of tacked on as some PM at Red Hat or PM at Google or whoever decided, hey, I want this. And then they fought to get their patches through all the lieutenants on the kernel team. And so the problem with containers being a sandbox of sorts is that it just simply wasn't designed as one. And we see all these escapes because, containers is espoused by Docker or espoused by Podman or espoused by, any of these other frameworks, there is no like create container to, there's no syscall that says create container. It isn't that. There's unshare. There's, apply this namespace flag. There's all this other stuff, but there is no like create container to. It's left up to, Docker or whoever to implement all these other things. And maybe they're not experts at dealing with all this. And so that's why we see that, to this day, things like Flatpak on Ubuntu, there's just known escapes that exist. Flatpak is totally insecure. People say, oh, it's a sandbox. It's not a sandbox. It's very easy to get out of. And those are just things that exist. And so again, that's just like another piece of software that uses container functionality. But since it's so different from, say, a Docker container, the functionality is exposed differently. And so to me, that's probably the main problem with container security. There's a lot of other things, but that's kind of the main thing. So sorry, going back to your question though, we talked about containers, micro VMs. It's another question that people ask. How is this different from a micro VM? The answer is that they are different, but they're not competitive. It's not like you have to choose micro VMs or unikernels. Micro VMs usually connotate that you're working with something like Firecracker, or there's another project, it's a fork of it called Cloud Hypervisor. And so that's usually what that connotates, is that you're using a different machine monitor, is what they're called, than something like QEMU. So QEMU is the machine monitor that the vast majority of people are going to be working with when they're working with VMs, if they're managing them themselves. But Hypervisor is another choice. And so Amazon is famous for saying, hey, we're going to use this for Lambda because we want our workloads to spin up really fast. And so what they do with Firecracker is that they trade boot time, like a decrease in boot time performance, for a little bit lower runtime performance. So they remove a bunch of functionality. For instance, with Firecracker, you can't, today anyways, they are kind of looking at changing this, but you can't talk to a GPU in Firecracker, for instance. So all these AI workloads, all these blockchain workloads, none of that really works in Firecracker. So that's why some people will use Cloud Hypervisor. But when you do that, you're adding more boot time. And so that's the reason why Firecracker doesn't have it. And so boot time is actually kind of a function of your disk image at the end of the day. The bigger it is, the longer it's going to take to boot. So if you give me like a little Go binary that's 30 megs, I can boot that in tens of milliseconds as a unikernel. If you give me a Python image with like 20 gigs of training data on it and it wants to load it all up at the same time, that's going to take a while. Same thing with you give me a JVM, like say we want to boot Elasticsearch. Elasticsearch takes a second to boot. And so if your whole thing is like, I want really fast boots, I want to pause and resume so fast, depending on the workloads, you're not going to get that benefit. And so you really need to look at like, can I actually benefit from this? But the other thing that Firecracker gives some people, and some people are using Firecracker for this reason, is going back to container security. There's just such a large concern about, container security, especially in like a multi-tenant situation. And multi-tenant is not just, I have multiple customers. It could also be, I work at a large insurance company and I have, 1,000 engineers and I just want to isolate each team's builds from each other. Simply because, maybe this team's software does have a security issue. It gets taken advantage of, but it doesn't instantly nuke the rest of your infrastructure because somebody had a breakout because it's contained in that VM. And so that's where that comes from. So we went over the containers and micro VMs. And then, obviously we have unikernels. So as I mentioned, you can run unikernels inside of Firecracker. For me, unikernels defining characteristics are really that it's a single application, single process system, and there's a complete lack of user land in the sense that there's no shell, there's no SSH. You can't start running other programs on it. This is a pretty big one, and that kind of sets the architecture for how you're using it. Now, some people will go back to like, say, the Mirage papers or so forth. And there was a lot of talk about, well, we're gonna skip the syscalls and so forth, and we're going to get a performance boost. So what we have found is that the performance boost is not from the kernel to user context switch. there is a cost associated with that, but it's not as large as the cost associated with having process A and process B switching out. And to kind of dive into that further, if I go to Amazon, I spin up an EC2 small right now running Debian or Ubuntu or something like that. There's going to be 100 processes all running on that same system, even without you doing a single sudo apt-get install. And yet you only have one vCPU available to you. So what's going on is Linux is switching amongst all these 100 processes, in kind of the blink of an eye. You don't even really know that it's going on, but that's what's going on. And every little switch, especially from process A to process B, that's actually a really expensive cost. And so you can characterize, there's kind of like 4 context switches. There's like user LAN process to user LAN process. There's a thread to a thread. There's a kernel thread to a kernel thread. There's a kernel to a user. So these are all different, and you have to explicitly state which one you're talking about to actually kind of compare the costs of each. And so just to be clear, we support multi-threading. So all the languages like Go and Rust and Java and C and all these languages that have access to the threads, you could totally use them. If you have 198 threads on a machine, you can use them all. So there's no limit there. It's just the limit on what we feel is an outdated architecture, and that is the idea of multiprocessing. Specifically, we're really talking about different applications. But even something like a Postgres, we think that's an outdated program. This idea that you're going to have a master process and then spawn like all these different child subprocesses. And this kind of goes back into our history lesson, right? So When did Postgres come out? Some people might say, oh, well, 94, but no, it came out in like the early 80s as Ingress. So that's when it was working on. And then it got rebranded a couple times. And then it finally got rebranded to Postgres around 94. But even in 94, again, we didn't really have threads, not usable ones. I mean, we had them, but they sucked. And we didn't have SMP machines, so you couldn't really use it anyways. It wasn't until around 2000, 2001 that we got an LTP inside Linux to where threading was actually worth a shit. And then also the commodity consumer SMP processors. Without those two things, threading was just not a thing you can do. And so when I was going to school back in the late 90s and the early 2000s, people had this notion. They're like, threading sucks. You shouldn't use threading. That's bad. But it was only a few years later that threading became the preferred thing. And now, when we're talking about big data or AI workloads or things like that, now we're starting to really suffer the consequences from this multiprocessing model. When you have heaps that are 30, 40, 50, 60 gigs large and you're forking those off, those are not cheap. And so there's a lot of problems with that programming model. And so our bet, if you will, with Unikernels is that, we're kind of changing hearts and minds on how you should architect your software. And so we're quite okay saying that, this is an outdated practice. And if you want to use something like a Postgres, you should convert it to threads, which, by the way, the Postgres authors are actually doing. We took some existing patches that existed and we touched them up a little bit, and we did make a Postgres unikernel. Now, others have talked about various Postgres unikernels, but this is where, when it comes down to what is a unikernel, I would challenge people on saying, hey, if it's just running Alpine Linux, well, that's not really a unikernel. It's just Alpine Linux running in a micro VM, right? And there's nothing wrong with that. Like, I'm not saying there's anything wrong, but that's not the same thing. It doesn't have the same architecture. It doesn't have the same security guarantees. There's a lot of like random things that are just not even close to the same. So that is one characteristic that I would say is there.
Very interesting. I mean, you talked about a lot of interesting points there, and I think the crux of it is that all of this is built on old technologies, and a lot of effort has gone on making it work on top of it. and then making it work for certain workloads without actually changing the abstractions, without actually changing the architecture, without actually going back to the first principles and thinking about what exactly we need in terms of abstractions, right? And that makes sense. You also mentioned like you compared like micro VM and unikernels and how they are not necessarily mutually exclusive, and you could run a unique in Firecracker. So that is good information. And you also mentioned about Postgres, which is a really popular database, and a lot of variants are coming up into the market. And you also mentioned, I know some people use micro VMs for Postgres deployments. I guess Prisma recently announced their Postgres, and it used unikernel. So there's a lot of nuance.
So I actually don't believe that, though. I think that's one of those ones that's running Alpine, and this is just my industry knowledge. But so as we touched on, like Postgres itself, first you have the multiprocessing, then you have the signaling. Postgres is what I would call the IPC poster child, System 5 IPC poster child, because there's so many different concepts that it uses because of the time period it was built in. Again, early 80s, then the 90s, that it's your kernel has to support quite a bit to run things unpatched. Not only that, but the kernel variant that you're actually going to use needs a file system that actually works. And I know for a fact that this particular one doesn't really have a suitable file system for running. But then there's other things that you can do where you can just go spin up this database and issue a few commands and get the information you need. So yeah, coming back to the definition of like what a unikernel actually is, running Alpine and Firecracker, I wouldn't say that fits the definition. But
is there
to each their own, I guess.
Yeah, is there a specification where we say should there be a specification to define a unikernel? I mean, otherwise it's a lot. It will be a lot about different opinions, different experiences, right? Like what is a unikernel and what is not.
I think, unfortunately, I don't know. I mean, maybe there's something that would happen like that in the future, but the term's been tossed around for a little bit too long. And, talking about various unikernel projects, there's over like 10 different projects. Pretty much most of them are abandonware. Again, a lot of them came from academia. And so it's very hard for, even when companies want to spin out of academia, it's very rare that actually happens. So we've seen lots of different people try to commercialize and so forth on it, and then they fail. And I think one of the reasons is, again, you're kind of fighting this like 30-year head start by Linux. So
yeah,
so you do have to be kind of like very precise on what workloads you're going to go after first, and then kind of throw stuff on.
Yeah. That makes sense. I was listening to one of your interviews probably a couple of years ago, so I don't know if that still holds. But you mentioned that there are multiple implementations of unikernels, and each of them are really different. It's not like they have similarities. So it almost felt like these are like different AI models tuned for different purpose.
That's a good analogy.
Yeah.
Yeah, so in the past, I've largely grouped things into like POSIX and non-POSIX, because early on, a lot of the stuff was very language specific. You would have things like Mirage that was OCaml only. So Mirage has been around for a long time, right? But you don't see a ton of people deploying it. Why? Well, not everybody writes OCaml. I can name Jane Street Capital in the US that writes OCaml, and that's about it.
Yeah.
So, there was one for Haskell. Okay, well, I know Glorious up in Portland. That's about all I know who writes Haskell. So there's things like that where it's very hard to popularize a language specific framework. Same thing with Erlang. I actually know more companies that use Erlang than those other two languages, but there was actually this project called Erlang on Zen. That was actually probably the first project that I saw that was, quote, a unikernel. It didn't even describe itself as that, but I saw that back in like 2012 or something. And that just fascinated me when I saw it, because you would like load a page and it would spin up a VM. I was like, wow. A lot of them are language specific, and those, at least from a commercial perspective, are just DOA. Now, in the POSIX camp, you have things like OSV, RumPrum was part of that. And what that really meant is, can I run my normal Linux application without making modifications. This is kind of, sometimes you make modifications, sometimes you don't, but in general, can it run without making modifications? And so that's the camp we kind of subscribe to. So we have an elf loader. You give us a Go binary, a Rust binary, JVM, whatever it is, we're going to load it up the same way as Linux does. It's just, there's a lot of stuff that we don't support. Like, you want to do a UID check. We don't do that because we don't got users. Sometimes you'll see patches that I've put in, not necessarily like a patch, but like a override of sorts. I think Elasticsearch I did this on. And so you'll have these daemons and they'll make sure you're running as root or something. Well, it's like, well, we don't have a user, so we'll just change it to something else. And what's really interesting about this, whenever I create these patches, is like people will do these checks, but then there's no check to ensure that the check was actually valid, right? So it's kind of interesting, this like security theater that you'll find in some code bases out there. That's a big thing that, again, that was another thing that was in the 90s, but that also kind of explains why this started too, because back in the 90s, people would have the notion of different users. They would have the notion of like the wheel group, and, you have different, all your admins in wheel and so forth. And so you would have this, and people paid closer attention to, access rights on files and so forth and all that. But that really got blown away with Amazon. Like, it really got blown away. Nowadays, like, you go to Google or Amazon, you spin up your image, and that user that you log in, which is not root, you can just sudo su in your root. And like, most people just use that. They don't do anything else to like try to lock that down or anything. And I think that's become so common. And to us, that's just an indication that that's been left behind. And so obviously it's not good. It's, what do you do? And so for us, it's like, well, if you're going to walk down that path, you should keep walking towards a unikernel to where you can't log in. You can't just start running random stuff. And if you want that ease of use, keep walking down the path towards unikernels, have the easy use, but get rid of that security issue that you've been dealing with.
Understood. That makes sense. So I think so far what we have discussed, it gives a good foundation about, the history, where are we coming from, what's going on, different terminologies and, comparisons and some misconceptions and variants of unikernels. What I understand is, okay, all these technologies and way of building applications and deploying them and maintaining them is built on top of old abstractions that probably do not make sense. And unikernel is an operating system. It's not just another trimmed down Linux. It's much more than that. There are obviously some limitations, and those limitations depend on different implementations of unikernels. But I'm now looking at NanoVM, right? And when I go to the website, it talks about, security and, performance, different performance boost in different cloud environments like AWS and GCP. And then, of course, the architecture changes, and there are some limitations mentioned, as you also mentioned about that there is no shell. You can't go and, run multiple processes. You can't just log in and run some random commands and so on. So I want to understand, how is NanoVM different from other unikernels?
Yeah.
And what do I get? Like, how did you start with it? Like, what was the architecture in mind that you kept while starting at it?
Yeah. So, like I said, I have a background in security, and so that's the world that I come from. I think I don't go to DEF CON anymore, but the DEF CON that I did go to, maybe the first one was in 98, 99. So that's, when they would be at smaller hotels and so forth. I've spoken at many of these security conferences, worked at many security conferences. Half of our cap table are security people. I come from that world. So I saw some of the benefits of this architecture, but also the way that people were implementing it. They were just, they weren't aware of some of the security issues that have been addressed in the past. So I'll go into some of them. So the idea of page permissions is a big one. And so that's actually one really large difference between Nanos, the kernel that we work on, and practically every other implementation out there. We do care quite a bit about things like page permissions and execute. We do care about a lot of these other things, not mapping null pages, lots of things like that. And so to drill on like page permissions, for instance, if your audience isn't familiar, you can have a user that has a file and you have read, write, execute for the user and the group and the world, right? So there's a similar concept, but it deals with memory. So when you execute your program, the program loads up in memory. And for Linux, you have the ELF binary, is the most common format. It used to be a.out, now it's ELF. And if you look at the ELF binary, there's certain bits of the program that are mapped in memory. And so they have different permissions. And so if I have a string literal, for instance, and like say a C binary, I have char star hello world and then printf that char star or whatever. That string literal, that's actually stored in read-only memory. Now I'm using that as an example, but that could be a SSL certificate. That could be, God forbid, a password through an environment variable or something like that. So basically the idea is that certain parts of the memory should only be read-only versus writable. Because if it's writable, then I can just overwrite it. And so in particular, code segments, bits of your code, you don't want some attacker to have the capability to just like start rewriting your program in memory. It's a really bad deal if you can do that. Because when a lot of people, when they think about exploits, they're thinking, oh, I'm just going to grab a shell, I'm going to curl some crypto miner, and that's my payload. And that is a very common payload. But again, like if I can just rewrite your program in memory, I can do whatever I want. And so that's assumption that we've had in Linux for over 20 years now. Is something that's been largely enforced by the distros very well. The problem is a lot of these unikernels totally broke that. And so if you go back 2019, I think, NCC Group, which is kind of a large security consultancy, they wrote like 100-page PDF and they just torched the crap out of unikernel security as a kind of thing. And, to this day, like a lot of those problems were not addressed in those projects. And so to me, when I'm talking to like a CISO or somebody else who cares about security, those projects, those companies, they're just totally dead on arrival if they don't have an answer to that concern, because it's such a large concern. So yeah, there's a ton of security primitives in a kernel that are kind of mandatory. They're not just nice to have, they're mandatory. And that's definitely like a really large differentiator for us. But I guess getting off the security side, the other thing that I point out is that we've been in market for quite a while now. And so we have tons and tons of different integrations and support for things that you just simply won't find elsewhere. GPU is one of them. So we ported NVIDIA's GPU driver over. This isn't something that remotes to a GPU. There are some unikernel projects that do this kind of like remoting, but that's a very different implementation, incredibly much slower. So we actually have like an actual real driver. And we don't just support the cloud GPUs like Amazon GPUs and Google's, but we also support commodity ones. So like one of our customers is a blockchain company and they don't run in the cloud. Why? Because it's too expensive to access the GPUs. And so they have like their own data center with their own GPUs. And we actually threw in commodity support for them. So that's another huge differentiator. And that's not like something that's super easy to add either. You didn't write the code. We didn't write the code, right? But you still have to maintain it. You still have to port it. And it's a chunk of work. Not only that, but if you look at our port of what we call a KLib, kernel library, we've made our own modifications to it. So we have string bounding throughout the Nano source code. This is, again, a kind of a security feature where we just want to bound pretty much all of our strings to prevent a certain type of security thing. And so we applied that to the kernel, to the NVIDIA library. And so automatically that's like not something, even if somebody like takes the code, they can't just integrate it into their project because there's like nano specific changes in there that are like freaking everywhere. So it'd be a large lift. Similarly, people might say, hey, you guys are using the LWIP networking component, right? And that is true. We forked LWIP a long time ago, but our fork has so much other support. So if you go to savannah.gnu.org, where the LWIP project is hosted, it hasn't really had updates forever. We tried to upstream some updates a few years back, and I think the authors are just, they don't really maintain it anymore. And so we eventually got to the point where we were like, well, we're not going to send any new patches in if they're not going to get accepted. And so when you see references to LWIP in our repo, just know that it's an extremely different LWIP. We have support for a lot more threading, for instance, which the upstream doesn't. We have stuff like one funny thing that's a security side, stock LWIP, you can just send flood to death. So send flood is basically you can just send traffic to it and bring that VM to its knees. And it's kind of funny because LWIP is also used in all these IoT projects. And it just kind of makes me wonder, like, how many of these routers and cameras and crap are susceptible to this send flood, because again, the stock LWIP is totally susceptible to it. So we have like tons and tons of fixes in there. And then I guess the architecture on Nanos is also pretty different. Some projects have tried to go down this like librarification route where they'll like make optimizations to kind of user land libraries. And I think that's interesting and definitely something worth exploring. When we talk about libraries, we're really talking about integrations. And so it's very typical, like when we go into a company, somebody gets a hello world working and then they want to push it out to prod. And then they immediately run into like all the various integrations that they have, because there's like 100 different APM vendors, 100 different logging vendors, 100 different security vendors. And they could probably hack something together. But then when they want a tighter integration, that typically is going to reside kernel side. And so who best to kind of write that integration and maintain it? It becomes us. And so that's kind of like where some of our commercial side kind of comes into play. But we've really kind of expanded that quite a bit. So we have like all these different integrations. In terms of support for clouds, this is something that I think people new to unikernels might not really realize. But again, being an operating system, every time we support a new instance type or a new cloud or whatever, we generally have to add support for the drivers. So the latest one I think was with Azure. They had a Gen 2 ARM instance. We had existing ARM support. We could deploy to RPIs. We could deploy to Amazon, Google's ARM. But this particular, I think it was Amper, we didn't have support for it. We had to add support. Sometimes there's networking. So like GVNIC on Google, that's Google's own networking driver. It's not using Vertio, it's using GVNIC. It's way better. It's awesome. But again, we had to add support for it. You're not going to find support for like almost any of this stuff in any of the other kernel projects. One of the reasons why is not because people can't do it. It's just we've been around for a while and we've added the support as customers have asked for it. So now you can deploy to like, 16 different clouds out there with NanoVMs. By far, like way more providers than any of the other projects that I'm aware of. So
that is very, very interesting. And when you were talking about, adding integrations and, you mentioned APM libraries, logging libraries, and I got a sense of the architecture, but I'm curious, when you add these integrations, what protects you from adding this bloat? So eventually, if you keep adding more and more features and more support, what is the architecture principle that you follow to avoid having this bloat?
So adjacent to unikernels, there's this idea of a library operating system. And I think, if you put us on the spectrum of library operating system and unikernel, we're a little bit more towards that library operating system phase. And it's not even something that we thought about doing. It just kind of happened. But essentially all these integrations that we mentioned, those are all entirely optional. And what's really interesting versus something, say, like Linux, where, Ubuntu might include like a ton of drivers by default because they just want it to work everywhere. What's interesting is Ubuntu caters towards that multi-process system. A lot of people run Ubuntu desktop, for instance. So not just server, but like their day-to-day use desktop. And so that has a different set of needs. But when we focus on making these only for a single application, and you can build and deploy these things in tens of seconds, that means that we can actually customize that image at the kernel level in tens of seconds as well. So turning on or off some sort of APM library integration, that's just a simple config item, and it doesn't take any time to turn on and off. It just happens. And so that's actually a really huge difference compared to doing the same thing on Linux where you install an agent and all that sort of thing.
Interesting. So I, as a developer, get the choice. What I want, I can enable by changing the configuration. And since the build time and deploy time is really low, I can do it very quickly and, change things. So it's not like I get a lot of things for free that I never intend to use, but it's more like reverse. If I intend to use something, I can add it. Okay.
I think just to drill in on this a little bit, I think some of the unikernel projects out there, they were looking at it's like, oh, well, you should have multiple networking options to use, like LWIP versus, some other networking option. And it's like, the average developer doesn't even know that exists.
Mm-hmm.
Like it's, if somebody wants to hack that in, that's great. But I don't think that's something that you want to expose as some sort of option to your average end user. I mean, to me, like, you have people who hack on the kernel, and then you have people that use it. And these are different groups of people. And so if you hack on it, knock yourself out. But if you're an end user, we don't really want to expose that level of complexity to people. One of our guiding things has been, we really want to keep things super simple. We want things to be super intuitive. We want things to be pragmatic. We're not, if it's Microsoft versus Apple, we're a little bit more Apple in that sense. Microsoft is like, yeah, do whatever, throw 300 freaking toggles on it. And Apple's like, no, this is the correct way. So yeah, I think we're a little bit on that side. The integration side, to me, again, that's just a config option. And if you go to like the ops website, for instance, and you go into the documentation, I mean, there's just infinite number of configuration that you can do. There's image configuration, there's instance configuration. A lot of this is cloud specific. So a very, very common question we get with people who want to use this, who've never used it before, is, well, what do you do for orchestration? And they're coming with this Kubernetes Docker mindset, and they haven't really experienced the unikernel mindset yet. And so they're confused, which makes sense. But if you look at this configuration, you start to see like, we have such tight integration with all these different clouds. So to be clear, we don't do any hosting whatsoever. Like we do zero hosting. We expect all of our users run on Google or Amazon or DigitalOcean or wherever they are running to begin with. And so we have all this really tight configuration that fits into some of these existing providers. Stuff that is exposed that wouldn't really necessarily be exposed on a Linux system. Just to drill in on that and give you an example, debugging, people were like, well, they might have read Brian Cantrell's article ages ago about unikernels are completely unsuitable for production, yada, yada. And he, goes into this diatribe about debugging and so forth. But in our view, debugging is actually much easier. I can go to Google Cloud and I can export the entire freaking unikernel. Like nanos.org is a Go unikernel running on Google Cloud. I can just export that thing either from the command line or from the GUI, and I can get my unikernel locally. I can attach GDB to it and I can find exactly what was going on. Or I can look at the core dump and I can find exactly what's going on. We debug stuff all the time in the cloud, like the site's not responding, and so it's obviously we fix bugs, right? How do you think we do that? We debug it. So like it's just different styles. But yeah. And so that's one thing that we really focus on is like very tight integrations. One of the recent users of ours, they said, oh, you should call yourself Cloud Native 2.0 or something, simply because we're so much more tighter with the clouds than a container system would be.
Yeah. That is powerful, actually. Cloud native I mean, it's a popular term, popular marketing term, so that could
Yeah.
actually be really powerful. Let's go to the other side of the world, right? So, okay, so in theory, we understand that the abstractions are really simple. I get what I really want. The footprint is really low. It's secure, and I think that's the main reason, because the footprint is so low that there is less open ends, right? Like people, less escapes that people can do. Performance, of course, because of the lower memory footprint and, requirements. There's only one process that runs. It's really tied with your application. I want to understand that as well. But from the developer's point of view, so let's say I am used to containerization and I use Kubernetes. I am running my workloads on production, right? And I have different types of workloads. I also run databases, I run web applications, and some AI applications as well. What should be my mental model when I want to try something like Unikernel or something like NanoVM? Where should I start to even understand, will it even work for my use case? What are going to be the challenges and limitations?
Yeah. So what we always suggest is first off, if you haven't like downloaded Ops, which is kind of a CLI tool to build and deploy these things, and there's also a desktop version if you like the GUI. That's like the first thing I would do is just download Ops and like try to run whatever language you want to use. Try the Hello World. We have examples for languages you haven't even heard of. So it's but try to run the Hello World. And we always say do the Hello World first, just so you get the mechanics down and you're not like fighting your understanding of the tool or anything. And then right after the Hello World, before you start porting your prod application over, which a lot of people just immediately want to dive into, and we say, okay, well, just take a breath and try taking that Hello World and push it out to whatever cloud you use. Amazon, Google, DigitalOcean. We don't really care where you host, but just try to replicate that environment. And once people do that, then they start getting this aha moment, because that's when they realize the whole orchestration question is not really a question at all. And they start to understand more of our philosophy. And what I mean by this is like by default, when we spin these things up on Amazon, the unikernel, so you take ops and you say, I have a Go web server. Input is a Go web server. Output is a disk image. And that disk image is only running that Go web server. There is no Linux, there's no k8s, there's no containers, there's nothing. We upload it to Amazon. This process takes like tens of seconds. Uploads. And then when we create an instance, it's literally creating an EC2 image instance out of the image that you uploaded. So EC2 boots up. Again, no Linux is running, no Kubernetes is running. It boots straight into that Go web server and it's instantly running. That's the only thing that's running. If you want to run your Postgres, you go boot that as a separate instance because everything's talking across the network today. This is one of these differences from the 90s when that was not the case. Back then, we might have Apache and MySQL on the exact same box. And so in that case, they might not be talking across the network. They might be using a Unix socket or something like that. And so that's one of these things that we're saying, hey, this is an outdated practice. This is not something that we think people should be doing anymore. And so, and a lot of people don't. They're just not thinking about it. Everything is talking across the network today. And so yeah, coming back to the orchestration side of things, though, when you spin up that instance and the image, you do ops image create, ops instance create. Process only takes few seconds. Then you realize that you're not actually managing the orchestration anymore. You can specify your volume and your networking and your security and all this sort of stuff, but you're not actually managing. And that's a huge weight off of people's shoulders because now they don't have like 2,000 lines of YAML. They don't have all this complex underlay and overlay networking. They don't have all this, weird storage mounting with their database that they have to pay attention to. They don't have to deal with any of that. It just kind of works out of the box because the big clouds have invested, untold amount of money. They have tens of thousands of engineers that know this way better than your small little team does. And you get to leverage all of that. But instead of running Linux and having to manage that, all you do is focus on your application. So it completely divorces the developer from managing that server. And it has this sort of platform as a service feeling. It has sort of this serverless feeling, but without all the kind of like band-aids that those platforms put on. And there's no third-party vendor too. That's another thing. Instead of paying like, and I'm not pointing fingers or anything, but like say instead of paying $30 to PlantScale or Vercel or somebody else, you can just run on a big cloud yourself and not have to deal with all that stuff. And there's no middleman. So it's very different feeling when people get into it. Now, I must say that this is not the only way to run it, but it is like the traditional way to do it. If your organization is all in Kubernetes, like say you work at a company that's like 600 people or 600 engineers or something, chances are you can't just immediately start doing this in prod. Chances are, besides the integrations, you're going to have to fit into the existing flow. And so having said that, you can run these under Kubernetes. You can use projects like KubeVirt. You can use there's other things that orchestrate VMs you can use. And then there's also things like one of our products, NanoVMs Inception, which allows you to run VMs on normal EC2 instances without a crazy performance hit. And so that's traditionally been something that's been people thought you just couldn't do. One of the things people have with Firecracker, they're like, oh, well, you can't run Firecracker on a normal VM. You got to go use a $4 an hour metal instance, or you got to go rack your own machines or something. So with Inception, you can actually run those on like just a normal T2, and it'll cost you 10 cents or 8 cents or whatever the cost is. So that's something that's very, very straightforward now. And to me, that unlocks like a whole bunch of new workloads, in my opinion, because now all these people that were like, maybe they were married to Kubernetes or something like that, it doesn't matter. Now they can just run those workloads and they don't have to deal with the whole nested virtualization tax anymore. So
very interesting. I mean, so apart from gaining the security and the performance boost, getting rid of all the ops work, I think it's a big win, right?
Yep.
You don't have to think about all the middle layers for orchestration that you have to maintain and do library versions and other stuff and maintaining all these YAML files that probably not everyone understands what's going on. They're just there. So I think it's a big win. Going into one EC2 instance that is running your image though, so there's just one process, right? But there is application running, there is kernel running. How does that interaction happen? So because we don't have like a kernel space and user space and all the other like older traditional way of doing things. So how does that work? Is it all like single process which runs the application and the kernel and the other integrations that I might have, or how is that structured?
So yeah, this is also something where we differ from a lot of other projects. We do have that distinction. And so earlier when I was talking about the context switching costs and how we found the user land process to process, that's the most expensive cost and that's what we killed. But we still do have a kernel user switch. And there is pretty important security reasons for that. So there's this thing called like an info leak, for instance, in security world. And an info leak is somebody in user land knows the address of some object in kernel space. And when you have that, you can basically map out the rest of the kernel. And if you get some sort of write primitive, then, that's where danger can happen. And so from a security point of view, we do have this. Now, you're asking how this actually works in practice. Well, it works very similar to Linux. On the kernel side, we do have some coroutines. Basically, when we started out, we didn't have like threading at the time. We do now, but essentially it's a way that we did in C because the kernel's in C, and it allows us to basically defer different chunks of work while we might go do an expensive operation like write to disk or something like that. So that's kind of how it works. Scheduling, as you might imagine, becomes a lot easier. So compared to Linux, again, Linux without you installing a single thing has like 100 processes running. And so I wouldn't say a lot of work has gone into scheduling, but there's like non-trivial amounts of code that deals with scheduling on general purpose operating systems. It's very different from a unikernel perspective because, again, there's only one program running. As soon as you break that kind of architectural decision, that's where you're going to have to start to invest in performance and so forth. And I think some unikernel projects have been like, oh, well, we should go down the multiprocess route. And I think that's severely misguided, because then if you go down that route, like, you're just Linux at the end of the day. And why would you even try to have the same thing as Linux? Because Linux is going to win, like to me, it doesn't make any sense. Like, you have to be different at the end of, like, you just have to be different. You're never going to make a Linux that's better than Linux.
Yeah, you're at least 30 years
we
behind.
can make a Nanos that's different and focuses on different problems and serves different workloads. And for those workloads, we can be better. And so, we have proof, like Go and Rust servers, they generally perform a lot better. The security front is way better. Now, your average developer doesn't, in my opinion, but your average developer just doesn't care or know a lot about the various security issues that exist. But, when you're talking to larger companies, they're aware of these issues, and they do care quite a lot. A JP Morgan, they spend billions and billions of dollars on security every year, which I'm glad they do, because they're like one of the biggest banks.
Right. Yeah. At least they should do. Yeah. Awesome. So I want to understand, what are the current limitations in terms of course, the development work that people need to do, and what are the limitations that you think can be fixed in the future, and some limitations that probably may not even work because, like, fundamentally different.
So I think the largest limitation that people run into, well, maybe there's two that I would say most people run into. One is packaging. So a lot of people are coming from like a Docker Kubernetes world. And so they're used to finding like pre-made images just ready to consume and so forth. So for software that they did not write, they're just looking for stuff that exists. And so that's not necessarily a unikernel problem. That's more of an ecosystem problem. Like there's nothing in the kernel that's preventing that. That's more of just somebody hasn't done the work. And so we do this on a case by case basis. If somebody asks for something, we'll create a package. Or, if we partner with them and they have something a little bit more involved, we help out in that respect. But that's definitely something that people are like, hey, I want to run this as a unikernel, and then they go look for an image and it doesn't exist. That's one. Integrations is another one. I told you there's everybody has 1,000 different APM vendors and login vendors and security vendors, and some things work out of the box. So like syslog, we have a syslog exporter that you can just plug in. It's a config line item, and that'll allow you to talk to like pretty much most of the logging stuff out there. But some people have more fancy logging setups. Maybe they want to do some pre-filtering type of whatever. And so now they want something that maybe in Linux might be a daemon that sits there and does the filtering and the sorting and all this sort of stuff. And so when they come to Nanos, they're like, oh, I don't have this. It's not that we can't add that. That would be another klib, right? But it just doesn't exist yet. And so again, it's a situation of like, okay, well, how important is it to you? Are you guys going to do it? Are you going to pay us to do it? Like that's kind of what that conversation really plays out into. To me, those are the two big things, and neither of them are really kernel specific. Things like Postgres, for instance, again, we made the patches, we applied them, we got that running. That was kernel specific. There's like, it wasn't just multiprocessing. There's like, we talked about signals. We talked about a few other things. There's multiple issues with a project like that to get it running as a unikernel. But just to point it out, it's not impossible. It's something that can be done. Things that are impossible would be desktop applications. So I think video games or browsers or any sort of desktop application, that's just not something we do. It's not something we're ever going to do. We're solely focused on server-side stuff. If it runs on a Linux server in Amazon today, that's our bread and butter. But we don't really touch anything like somebody wants to run some sort of desktop application. That's just not what we do. And so that's a huge difference, right, compared to Linux, because Linux isn't just used for server-side stuff. It's used for phones. It's used for laptops. It's in your car. Mm-hmm. It's in a satellite. It's used everywhere. To us, that's also one of its kind of Achilles heels. it is because it is used everywhere. We're really drilled in and focused on only server side software.
Otherwise, you will end up probably reinventing Linux in a way because you will need.
Exactly. And so like when people complain and they're like, oh, well, I want to run multiple programs on the instance, it's like, well, go use Linux. That's not what we do.
Yeah, and probably that is a good time to ask why, right? Why do you want to do it?
Yeah. And we do have those conversations.
Okay.
And typically, for us, typically that turns into more of an architectural review. It's like, well, let's compare, the benefits and look at the contrast and see what we're gaining from each sort of thing. But generally, when we look at it, it's kind of like, well, you're already basically provisioning your applications as unikernels, but you're using Linux. So we're just more of a better fit for people who are provisioning all these different services on Amazon. And it's a more natural fit. And to us, we're still in like I know our company's been around for a while. People probably heard the term unikernels for a while. I think we're still very much in the early innings of this ecosystem. There's just so much untapped value. Actually, I think it was over at TU over in Germany. I forgot which. There's a lot of work with unikernels and databases right now coming out of research, and there's all these pointed questions that they have, and they're like, well, do we really need this kind of like POSIX semantics for a cloud native database? And when I say cloud native, I'm not talking about cloud native computing foundation. I'm talking about like very tightly integrated database, things like maybe a DBOS or something like that. And it's, I think there's a lot of really interesting work that can happen there when people kind of untie themselves from the shackles of this operating system that was meant to run on a physical machine. Might be a good time to point out, we don't run on physical machines at all. Nanos can only deploy as a VM. So that's just like an architectural constraint that we have artificially imposed upon everything. So there's never a case where, and we get this question, they're like, can I just go flash this server with nanos? And we're like, no, it's only a VM. So you can go run it on KVM if you want, or you can deploy it to the cloud, but there's never a scenario where we're going to run directly on real hardware. If you want to do that, use Linux.
Yeah, that's not the problem you're trying to solve, and it makes sense. That's cool. What's coming up in the future?
Yeah, I mean, there's lots of interesting things coming down the pipeline. Some of them we're saving as surprises. There's one in particular that's going to drop here soon that I think a lot of people are going to be interested to understand what kind of drugs we were taking. But so yeah, there's some interesting stuff. But there's also just like we're constantly adding new support for new things and leveraging different things, and there's so many different. Well, I can talk about some of them, like profiling, for instance. We have great profiling support in the form of like strace and k8s and ftrace, all these different tracings and sanitizers and so forth. And we're making tighter integrations with like our desktop to make it like really point and click easy. I had a demo the other day where I was just trying to answer a question like, how easy can we make it from a perspective of deploying these things? And so I made a little desktop shortcut that you can click on and it just deploys to Amazon by clicking on the shortcut. So, and there's lots of interesting untapped things that we can do here. This kind of mimics one of our investors was involved in this company called Thinstall. It sold to VMware a long time ago. And basically they did this on Windows, and it was basically a virtualized application. But it makes the idea of provisioning less of an ops thing, and it opens it up more towards anybody can kind of work on it type of thing. And so there's lots of interesting cases where we can kind of get rid of a lot of ops toil that exists today and just like make it more accessible to people. Maybe there's different workflows that change because of that. Maybe instead of having this gigantic, 2-hour CI/CD pipeline that, kicks out builds here and there and does all this stuff, maybe that simplifies in the future because some of the tooling gets exposed in a different manner. I don't know. There's a lot of software infrastructure problems that people are just simply not because maybe they think all the problems have been solved. Rob Pike himself had that famous paper in like 2001, operating system research is dead or something like that. And I don't think he was talking shit. He was just kind of decrying the state of things. And that was like 20 years ago. He was just saying, man, I wish people would, be more interested in this, work on this sort of stuff a little bit more, because there's so much untapped value. And I think with unikernels, with our tighter integration with all these different clouds, we can enable people to actually do these things in a manner that they haven't been doing before. A lot of these there's maybe some downsides to other companies out there, and I'll be honest about it. I think a lot of these platform providers, maybe they're not going to enjoy so much of that anymore. A lot of the SaaS stuff, if you look at most SaaSes today, they make a big point of like, hey, we're doing the hosting for you and that's why you pay us. But the reality is, like, man, there's not so much work involved when deploying unikernels. The application works or it doesn't. I can see lots of different people making their various plugins and so forth to tack on additional monitoring or whatever. I think there's so much untapped potential here that we're consistently enabling more and more of as we flesh out newer and newer features. So I would see that, to answer your question, I would see that more in the form of the k8s list growing quite substantially, or packaging growing substantially, things of that nature.
Awesome. I love it, because it's like going back to like the basics and building something from scratch that could actually work for the cloud environments, and get rid of all the bloats that we have around infrastructure, around the operating system, the images, the processes around operating those infrastructure, and security audits, and it just adds a lot of stuff, because you have a lot of things that you don't really need to run your application. And I really look forward to all the advancements and the features that are coming up generally, and also in NanoVMs. But yeah, I would love to follow the progress. And with that, I have a next question. How do we follow the progress that is happening in NanoVM or in unikernel space? What is the best way?
Yeah, so lots of different ways. We have a small YouTube channel we post videos every week on. We've got Twitter is somewhat active. My LinkedIn is honestly maybe the most active, and our engineering blog, if you like more in-depth technical content. We actually have kind of two blogs. We split it apart because we wanted the engineering one to be like only engineering, and then the other ones can be not so much engineering, but they're both good to kind of understand where our head's at, what things are going on. Most of the really cool features we try to announce and so forth. The GitHubs, obviously, both Ops and Nanos are open source. Apache 2 means you can do whatever the hell you want with them. And we actually have some other open source projects too as well. But yeah, those are some of the places that I would look at. Yeah, and just just download Ops, try out a Hello World, try deploying it to Amazon or wherever. And once you go through those steps, you'll understand what all the hub's about. So
yeah. I'll also make sure I attach all the links in the description below whenever it is released on YouTube and other podcast channel mediums. But yeah, look, thanks a lot. I really enjoyed the discussion. It was really insightful. I got really better understanding than what I had before recording this. So thanks a lot for joining me today. I really hope that this picks up really quickly, and there is more development also around the ecosystem, because the limitations that you mentioned were mainly around the ecosystem and not the unikernel itself. So I really hope to see a lot of advancements there. Yeah, probably we'll do another podcast episode whenever there is more development, whenever there is more, probably in the future and probably next year. But yeah, looking forward to it.
all right. Well, thanks for having us.